Beneath the surface of our planet lies a hidden force capable of reshaping the world in an instant. Supervolcanoes, far more powerful than regular volcanoes, have the potential to alter climates, devastate ecosystems, and even threaten the future of human civilization. Unlike the more familiar cone-shaped volcanoes that spew lava and ash in localized eruptions, supervolcanoes remain largely unnoticed, building pressure for tens of thousands of years before releasing energy on a catastrophic scale. These sleeping giants are not defined by their towering peaks or frequent activity, but rather by the sheer magnitude of their eruptions. A supervolcano eruption is classified as any volcanic event that ejects more than 1,000 cubic kilometers of material. That is thousands of times more powerful than a typical volcanic eruption. Instead of creating dramatic lava flows, supervolcanoes often collapse in on themselves, forming vast depressions called calderas. These calderas, often spanning dozens of miles, are the only visible reminders of past eruptions, masking the immense power that lies beneath. Unlike regular volcanoes, which erupt more frequently and often provide clear warning signs, supervolcanoes can remain dormant for hundreds of thousands of years. Their eruptions are so rare that no human civilization has ever witnessed one firsthand. But the geological record reveals a history of catastrophic events that have shaped continents, driven species to extinction, and plunged the planet into volcanic winters lasting years. Some of the most well-known supervolcanoes include Yellowstone in the United States, Toba in Indonesia, and Taupo in New Zealand. Each has erupted in the distant past, leaving behind landscapes permanently altered by their power. Today, these sites remain active, with magma chambers slowly refilling beneath the surface. Scientists monitor them closely, searching for any signs that another eruption could be on the horizon. Understanding supervolcanoes requires looking deep into the Earth's structure. At their core, they are fueled by immense magma reservoirs hidden beneath the crust. Unlike smaller volcanoes, which typically have a single, direct conduit for magma to rise, supervolcanoes have vast networks of interconnected magma chambers, allowing them to accumulate enormous amounts of pressure over thousands of years. As magma rises from the mantle, it gradually heats the surrounding rock, melting more material and increasing the size of the chamber. Over time, this process builds a reservoir of molten rock so vast that when it erupts, it can eject enough material to cover entire continents in ash. A supervolcanic eruption is not just an explosive event. It is a planetary-scale disaster. When a supervolcano erupts, the immediate effects include pyroclastic flows, fast-moving currents of hot gas and volcanic matter that can travel hundreds of miles per hour, incinerating everything in their path. But the real danger comes from the vast quantities of ash and gas that are propelled into the atmosphere. Volcanic ash is not like the soft ash from a fire. It is composed of tiny, jagged particles of rock and glass that can collapse buildings, clog engines, and suffocate living creatures. The most far-reaching consequence of a supervolcanic eruption is its impact on the climate. When sulfur dioxide and ash enter the stratosphere, they reflect sunlight away from the Earth, leading to global cooling. This phenomenon, known as a volcanic winter, can disrupt weather patterns, shorten growing seasons, and cause widespread crop failures. Historical records of smaller volcanic eruptions, such as the eruption of Mount Tambora in 1815, show how even a single large eruption can lead to devastating famines and societal collapse. A supervolcano eruption would be many times worse. Despite their destructive potential, supervolcanoes remain one of the least understood geological phenomena. Scientists rely on a combination of satellite monitoring, seismic activity measurements, and chemical analysis of volcanic gases to study them. However, predicting when a supervolcano will erupt remains a challenge. Unlike regular volcanoes, which often exhibit clear warning signs such as increased tremors and gas emissions, supervolcanoes operate on timescales that make detection difficult. The buildup of pressure in a magma chamber can take tens of thousands of years, and small changes in activity do not always indicate an imminent eruption. One of the biggest concerns about supervolcanoes is their unpredictability. While researchers have identified the world's largest calderas and mapped their past eruptions, there is no precise way to determine when the next eruption will occur. Some scientists believe that we are overdue for a major supervolcanic event, but whether it will happen in our lifetime or thousands of years from now remains uncertain. Modern society is more vulnerable than ever to a supervolcano eruption. Unlike ancient civilizations that could migrate or adapt to changing climates, today's interconnected world relies heavily on stable weather patterns, agriculture, and global supply chains. A volcanic winter could disrupt food production on a massive scale, leading to shortages and economic collapse. The sheer amount of ash in the air could ground flights worldwide, disrupt communication networks, and make large portions of the planet uninhabitable. Despite the risks, supervolcanoes do not receive as much public attention as other natural disasters. Earthquakes, hurricanes, and tsunamis occur frequently enough that they remain in public consciousness, while supervolcanoes are so rare that they are often dismissed as theoretical threats. But the geological evidence is clear. Supervolcanoes have erupted before, and they will erupt again. The only question is when. As we explore the history of these hidden giants, we will uncover the true scale of their power, the evidence of past eruptions, and the cutting-edge research being conducted to understand them. While the idea of a supervolcano eruption may seem like the plot of a science fiction movie, it is a real and inevitable part of Earth's natural cycles. In the next chapter, we will examine how scientists classify and identify supervolcanoes, exploring the methods used to determine whether a volcanic system has the potential for a supereruption. Understanding the science behind these massive geological features is the first step in preparing for their potential impact on the future of our planet. How supervolcanoes form. Supervolcanoes are among the most powerful forces of nature, yet their formation is a slow and complex process that unfolds over hundreds of thousands to millions of years. Unlike typical volcanoes, which build up through repeated eruptions of lava and ash, supervolcanoes develop massive underground magma reservoirs, silently growing in size and pressure until an eventual eruption reshapes the landscape. Understanding how these colossal volcanic systems form requires a deep dive into the geological forces at work beneath the Earth's surface. At the heart of every supervolcano lies a vast chamber of molten rock, or magma. This magma originates in the Earth's mantle, the semi-solid layer beneath the crust that extends thousands of kilometers below the surface. Supervolcanoes form in regions where magma accumulates faster than it can escape, creating enormous underground reservoirs of molten rock. Unlike smaller volcanoes, which have relatively direct pathways for magma to reach the surface, supervolcanoes trap magma in deep chambers, allowing pressure to build over tens of thousands of years. The process begins with the movement of tectonic plates. The Earth's crust is broken into massive plates that float atop the semifluid mantle. These plates are constantly shifting, driven by currents of molten rock deep within the Earth. When plates collide, pull apart, or slide past each other, they create the conditions necessary for magma to rise. Some supervolcanoes form over hotspots, where plumes of molten rock rise from deep within the mantle. Others develop in subduction zones, where one tectonic plate is forced beneath another, melting rock and fueling volcanic activity. One of the best examples of a hotspot supervolcano is Yellowstone in the United States. The Yellowstone supervolcano sits atop a mantle plume that has existed for millions of years. As the North American plate moves over this stationary hotspot, magma slowly accumulates beneath the surface, creating a massive underground reservoir. Over time, this buildup of magma has led to several catastrophic eruptions, with the last supereruption occurring around 640,000 years ago. In contrast, Toba in Indonesia is an example of a subduction zone supervolcano. Indonesia sits on the Pacific Ring of Fire, a region of intense volcanic and seismic activity caused by the movement of tectonic plates. Here, the Indo-Australian plate is being pushed beneath the Eurasian plate, causing magma to rise and accumulate beneath the crust. This process led to the formation of the Toba supervolcano, which erupted around 74,000 years ago in one of the largest volcanic events in Earth's history. As magma accumulates in a supervolcano's chamber, the pressure slowly increases. However, unlike regular volcanoes that periodically release pressure through smaller eruptions, supervolcanoes often remain sealed until the pressure becomes too great to contain. The weight of the overlying rock initially prevents magma from escaping, but over time, the increasing temperature and pressure cause the surrounding crust to weaken. Eventually, a tipping point is reached where the crust can no longer contain the immense force building beneath it. One of the key characteristics of supervolcanoes is their ability to form massive calderas rather than the cone-shaped peaks associated with regular volcanoes. A caldera is a vast depression that forms when a supervolcano erupts and the emptied magma chamber collapses under its own weight. Unlike traditional volcanic eruptions, where magma is expelled from a single vent, supervolcanoes often experience ring-fault eruptions, where magma bursts forth from multiple cracks in the Earth's crust, creating widespread devastation. When a supervolcano erupts, it ejects thousands of cubic kilometers of material in a matter of hours or days. The force of the eruption can blast rock and ash high into the stratosphere, with debris traveling thousands of kilometers from the eruption site. This widespread distribution of volcanic material is one of the defining features of supervolcano eruptions. Even after an eruption, the magma chamber beneath a supervolcano does not disappear. Instead, it begins the long process of refilling as magma continues to rise from the mantle. Some supervolcanoes experience resurgent doming, where new magma inflates the caldera over time, creating a dome-like uplift in the landscape. These resurgent domes can be an early warning sign that a supervolcano is becoming active once again. One of the most studied examples of resurgent doming is found in Yellowstone National Park. In recent decades, scientists have observed that sections of the Yellowstone caldera are rising at an accelerated rate, indicating that magma is slowly refilling beneath the surface. While this does not mean an eruption is imminent, it highlights the dynamic nature of supervolcanoes and the need for continued monitoring. Despite their destructive potential, supervolcanoes play an important role in shaping the Earth's surface. Their eruptions contribute to the formation of new land, enrich the soil with minerals, and influence long-term climate patterns. Many of the world's most fertile regions, including parts of Indonesia and New Zealand, owe their rich volcanic soil to past supervolcanic activity. However, the same forces that make these regions agriculturally valuable also pose significant risks for the future. The slow and unpredictable nature of supervolcano formation makes it difficult to determine when the next major eruption will occur. While some scientists believe we are overdue for a supervolcanic event, others argue that predicting these eruptions is nearly impossible due to the immense timescales involved. What is certain is that supervolcanoes will continue to shape the Earth, just as they have for millions of years. In the next chapter, we will explore the history of supervolcano eruptions, examining past events that have altered the course of life on Earth. By looking at these ancient disasters, we can gain valuable insights into what might happen if a supervolcano were to erupt in the modern world. The aftermath of a supervolcano eruption. A supervolcano eruption is one of the most devastating natural disasters imaginable, with effects that extend far beyond the initial blast. Unlike regular volcanic eruptions, which can cause local destruction but often leave surrounding regions largely intact, a supervolcano has the potential to alter global climate, disrupt ecosystems, and trigger widespread societal collapse. The sheer scale of destruction is difficult to comprehend, yet studying the aftermath of past supervolcano eruptions gives us insight into what could happen if another were to occur today. The most immediate impact of a supervolcano eruption is the massive explosion itself. When a supervolcano reaches its critical pressure point, the eruption releases thousands of cubic kilometers of molten rock, gas, and ash into the atmosphere. The explosion can be heard thousands of kilometers away, and shockwaves radiate outward, toppling forests and structures in an instant. Entire regions can be erased from existence, with anything within a few hundred kilometers of the eruption site facing total devastation. The pyroclastic flows, the fast-moving clouds of superheated gas and volcanic debris, are among the deadliest aspects of a supervolcano eruption. These flows can travel at speeds of over 700 kilometers per hour, incinerating everything in their path. Unlike lava flows, which move relatively slowly and can sometimes be avoided, pyroclastic flows engulf entire regions within minutes, leaving behind a barren, ash-covered wasteland. Beyond the immediate destruction, the vast quantities of volcanic ash expelled during the eruption create a different kind of catastrophe. Volcanic ash is not like the soft ash from a fire. It consists of microscopic shards of glass and rock that can cause severe respiratory problems, damage electronics, and collapse buildings under its weight. Even a thin layer of ash can be deadly, contaminating water supplies, killing crops, and rendering entire cities uninhabitable. The ash cloud from a supervolcano eruption can stretch across continents, affecting regions thousands of kilometers from the eruption site. But the most far-reaching and long-lasting effect of a supervolcano eruption is its impact on the global climate. When massive amounts of sulfur dioxide and ash are injected into the stratosphere, they reflect sunlight away from the Earth, causing a dramatic cooling effect known as a volcanic winter. Historical volcanic eruptions have demonstrated how even smaller events can disrupt global weather patterns for years. One of the most well-documented cases of volcanic climate disruption occurred in 1815 when Mount Tambora erupted in Indonesia. The eruption ejected around 160 cubic kilometers of material into the atmosphere, massive by normal volcanic standards but still far smaller than a true supervolcano eruption. The following year, 1816, became known as the year without a summer, with temperatures dropping across North America and Europe. Crops failed, leading to widespread famine and economic collapse. If a full-scale supervolcano eruption were to occur, the effects would be far more extreme, potentially lasting for decades. The Toba supereruption, which occurred around 74,000 years ago in Indonesia, is believed to have caused one of the most severe volcanic winters in Earth's history. Some scientists estimate that global temperatures dropped by as much as 5 degrees Celsius, leading to widespread droughts and food shortages. There is even a theory that the Toba eruption nearly wiped out early human populations, reducing our species to a small number of survivors. While this bottleneck hypothesis is still debated, it underscores the catastrophic potential of supervolcanoes. In addition to temperature drops, a supervolcanic eruption would disrupt rainfall patterns, leading to prolonged droughts in some regions and catastrophic flooding in others. The effects on agriculture would be devastating. Crops depend on stable growing conditions, and even minor shifts in temperature and precipitation can lead to massive food shortages. A supervolcano eruption could trigger global famine, as entire agricultural systems collapse under the strain of unpredictable climate conditions. The impact on human civilization would be profound. Modern society relies on interconnected global supply chains, advanced infrastructure, and stable climate conditions to function. A supervolcano eruption could disrupt all of these in an instant. Air travel would be grounded due to the thick ash cloud in the atmosphere, making transportation nearly impossible. Communication networks could fail as satellite signals are disrupted. Power grids, already vulnerable to extreme weather, could collapse under the strain of sudden environmental changes. Mass migrations would likely follow, as people flee uninhabitable regions in search of food and resources. Countries unprepared for large-scale refugee movements could face political and social upheaval. Economies would spiral into chaos as food prices skyrocket and essential goods become scarce. Even nations far from the eruption site would feel the effects, as global trade networks grind to a halt. The environmental impact of a supervolcano eruption would last for centuries. Ecosystems that took millions of years to develop could be wiped out in a matter of days. The destruction of forests, grasslands, and entire habitats would lead to the extinction of countless species. Marine ecosystems would also suffer, as ash and debris disrupt ocean currents and acidify the water. While the Earth has always recovered from past supervolcano eruptions, the timeline for such recovery is measured in thousands, if not millions, of years. Despite the catastrophic consequences, life on Earth has always found a way to adapt and endure. The planet has survived multiple supervolcano eruptions, ice ages, and mass extinctions, and yet life persists. If a supervolcano were to erupt today, humanity would face immense challenges, but our advanced technology, scientific knowledge, and global cooperation could improve our chances of survival. In the next chapter, we will examine the historical supervolcano eruptions that have shaped the Earth, looking at the evidence left behind and what it tells us about the future. By understanding the past, we can better prepare for the possibility that one of these sleeping giants may awaken once again. Supervolcanoes that shaped the Earth. Throughout Earth's history, supervolcanoes have erupted with unimaginable force, leaving behind scars that still shape the planet today. These eruptions have triggered mass extinctions, altered global climates, and changed the course of evolution. While no human civilization has ever witnessed a true supervolcanic eruption, the geological record provides clear evidence of their devastating impact. By studying the past, scientists can better understand what might happen if another supervolcano were to erupt in the future. One of the most infamous supervolcano eruptions in Earth's history is the Toba supereruption, which occurred in present-day Indonesia around 74,000 years ago. The eruption of the Toba caldera was one of the largest known explosive volcanic events, ejecting an estimated 2,800 cubic kilometers of volcanic material, nearly 3 times the amount of the next largest known eruption. The immediate impact was catastrophic, covering much of South Asia in thick layers of ash and triggering a volcanic winter that lasted for years. Toba's eruption is often linked to a dramatic global cooling event, with some estimates suggesting that temperatures dropped by as much as 5 degrees Celsius. This cooling would have disrupted ecosystems worldwide, leading to severe droughts and food shortages. Some researchers propose that the Toba eruption caused a genetic bottleneck in early human populations, reducing the number of Homo sapiens to just a few thousand individuals. While this theory remains debated, there is no doubt that Toba's eruption had a profound effect on the planet. Another major supervolcanic event occurred approximately 640,000 years ago in what is now Yellowstone National Park in the United States. The Yellowstone caldera is one of the most well-studied supervolcanoes in the world, and its eruptions have had lasting effects on the North American continent. The last major eruption of Yellowstone released over 1,000 cubic kilometers of material, blanketing vast portions of North America in volcanic ash. This eruption formed the modern Yellowstone caldera, a massive depression spanning nearly 70 kilometers in diameter. Although Yellowstone has not erupted on a supervolcanic scale in hundreds of thousands of years, scientists monitor it closely for signs of activity. The region is still geologically active, with geysers, hot springs, and seismic activity indicating that magma is present beneath the surface. While an eruption is not expected anytime soon, the possibility remains that Yellowstone could one day experience another massive event. Moving to New Zealand, the Taupo supervolcano is another example of a colossal eruption that shaped the surrounding landscape. Around 26,500 years ago, Taupo erupted in what is now known as the Oroonui eruption, ejecting more than 1,170 cubic kilometers of volcanic material. The eruption devastated much of New Zealand, altering the country's topography and forming the massive Lake Taupo, which sits within the caldera left behind. The Taupo volcanic zone remains highly active, with smaller eruptions occurring as recently as 1,800 years ago. While these later eruptions have not reached supervolcanic levels, they serve as a reminder that the system is still active. Scientists closely monitor Taupo for any changes that might indicate a future eruption. One of the oldest and most significant supervolcanic events in Earth's history took place nearly 252 million years ago in what is now Siberia. The Siberian Traps eruption was not a single explosive event but rather a prolonged period of intense volcanic activity that lasted for hundreds of thousands of years. This event released massive amounts of carbon dioxide and sulfur dioxide into the atmosphere, leading to drastic climate changes. The Siberian Traps eruption is widely believed to be a major contributing factor to the Permian-Triassic extinction event, also known as the Great Dying, the most severe mass extinction in Earth's history. During this period, an estimated 96% of marine species and 70% of terrestrial species went extinct. The release of volcanic gases likely caused acid rain, ocean acidification, and a significant depletion of oxygen levels in the oceans, making survival nearly impossible for many forms of life. Another significant supervolcanic event occurred around 120 million years ago with the Ontong Java Plateau eruption. Unlike explosive eruptions, this event was a massive flood basalt eruption, covering an area larger than Alaska in volcanic rock. Though not as well known as Yellowstone or Toba, this event likely played a role in shaping ocean chemistry and influencing global climate patterns. Each of these supervolcanic events had lasting effects on the planet, from changing landscapes to triggering climate shifts that influenced evolution. While some supervolcanoes erupt only once before becoming dormant, others, like Yellowstone and Taupo, have experienced multiple eruptions over time, suggesting that they may erupt again in the future. The question remains, could another supervolcano erupt in our lifetime? Scientists are working tirelessly to monitor known supervolcanoes, using satellite imagery, ground-based sensors, and chemical analysis of volcanic gases to detect warning signs. While eruptions are difficult to predict with absolute certainty, understanding the past provides valuable insights into the potential consequences of a future eruption. In the next chapter, we will explore the cutting-edge technology and methods scientists use to study supervolcanoes. From seismic imaging to gas emission monitoring, these tools help researchers piece together the mysteries of these hidden giants and assess the risks they pose to our world. How scientists monitor supervolcanoes. Supervolcanoes are among the most unpredictable and potentially devastating natural disasters on Earth. Unlike hurricanes, earthquakes, or even regular volcanic eruptions, they do not follow a consistent pattern, making prediction extremely difficult. However, scientists have developed sophisticated methods to monitor these colossal geological systems, tracking subtle changes that may indicate an impending eruption. Through seismic activity, ground deformation, gas emissions, and satellite imaging, researchers can gain critical insights into the behavior of supervolcanoes, offering humanity its best chance of early warning. One of the primary tools used to monitor supervolcanoes is seismology, the study of earthquakes and underground vibrations. When magma moves beneath the Earth's surface, it creates small tremors known as volcanic earthquakes. These tremors can vary in intensity and frequency, providing clues about the activity of a supervolcano's magma chamber. In areas like Yellowstone and Campi Flegrei, seismic sensors are placed throughout the caldera to detect even the faintest signs of movement. One key indicator scientists look for is harmonic tremor, a continuous, rhythmic vibration caused by magma forcing its way through cracks in the rock. Unlike typical earthquakes, which produce short, sudden jolts, harmonic tremors signal sustained underground activity, often preceding volcanic eruptions. While the presence of harmonic tremors does not guarantee an eruption, an increase in their intensity or duration is a cause for concern. Another critical method of monitoring supervolcanoes is ground deformation analysis. When magma accumulates beneath the surface, it causes the land above to rise or fall, creating measurable changes in elevation. Scientists use GPS sensors and satellite radar imaging to detect even the slightest shifts in the ground. A prime example of this occurred in Yellowstone, where researchers have observed sections of the caldera rising by several centimeters per year. While this uplift does not necessarily mean an eruption is imminent, it confirms that magma is actively moving beneath the surface. In the past, rapid ground deformation has been associated with major volcanic eruptions, making this a crucial area of study. Gas emissions provide another valuable window into the activity of supervolcanoes. As magma rises, it releases gases such as carbon dioxide, CO2, sulfur dioxide, SO2, and hydrogen sulfide, H2S. These gases escape through cracks in the Earth's surface, and their levels can fluctuate dramatically in the lead-up to an eruption. Scientists use spectrometers and gas monitoring stations to measure the concentration of volcanic gases in real time. A sudden increase in sulfur dioxide, for example, may indicate that fresh magma is approaching the surface. In places like Campi Flegrei in Italy, scientists have recorded rising CO2 levels, prompting concerns that the caldera could be awakening from its long dormancy. In addition to ground-based monitoring, satellite technology has revolutionized the way scientists study supervolcanoes. Satellites equipped with infrared sensors can detect heat anomalies, while radar imaging tracks surface deformations over vast areas. These remote sensing tools allow researchers to monitor multiple supervolcanoes simultaneously, providing a global picture of volcanic activity. One of the most groundbreaking techniques used in modern volcanology is muon tomography. This method involves using cosmic rays, high-energy particles from space, to create 3D images of underground magma chambers. By analyzing how these cosmic rays pass through rock, scientists can map the size and shape of magma reservoirs with unprecedented accuracy. This technique has already been applied to Mount Vesuvius and is being explored for potential use in monitoring supervolcanoes. Despite all these advances, predicting when a supervolcano will erupt remains a monumental challenge. Unlike smaller volcanoes, which often show clear warning signs before an eruption, supervolcanoes can experience long periods of activity without culminating in an explosive event. Some calderas have exhibited signs of unrest for decades without erupting, making it difficult to determine whether a major eruption is truly imminent or if the system is simply going through natural cycles of activity. This uncertainty has led to intense debate among volcanologists about what constitutes a true warning sign of a supervolcano eruption. Some believe that a combination of increased seismic activity, rapid ground deformation, and a spike in gas emissions could indicate an impending event. Others argue that these factors alone are not enough and that a supervolcano may require additional triggers, such as changes in tectonic stress, before an eruption occurs. Governments and scientific organizations around the world are investing heavily in early warning systems to detect volcanic activity as soon as possible. The Global Volcanism Program, run by the Smithsonian Institution, maintains a database of active volcanoes and works with agencies like NASA and the United States Geological Survey, USGS, to track potential threats. Meanwhile, supervolcanoes like Yellowstone, Toba, and Campi Flegrei are under constant surveillance, with teams of scientists analyzing data in real time. Despite our best efforts, there is no foolproof way to predict when or where the next supervolcanic eruption will occur. However, continued advancements in technology and scientific understanding bring us closer to unraveling the mysteries of these powerful geological forces. In the next chapter, we will explore the possible scenarios of a modern supervolcanic eruption, how it might unfold, the global response, and the long-term consequences for civilization. Through simulations and expert analysis, we will consider how humanity might face the ultimate test of survival against nature's most powerful force. What would happen if a supervolcano erupted today? A supervolcano eruption in the modern world would be an unprecedented disaster, one that could reshape nations, disrupt global civilization, and trigger a cascade of crises unlike anything in recorded history. While smaller volcanic eruptions have caused significant disruptions in the past, a true supervolcano eruption would be exponentially more devastating, affecting everything from agriculture and air travel to economies and geopolitics. The eruption itself would begin with early warning signs, weeks, months, or even years of increased seismic activity, ground deformation, and rising gas emissions. Scientists would likely detect these signals and issue alerts, but there would be no way to stop the inevitable. As magma built up beneath the surface, pressure would continue to rise until a critical breaking point was reached. Then, the eruption would begin. A massive explosion would rip through the landscape, ejecting thousands of cubic kilometers of molten rock, ash, and gas into the sky. The immediate blast zone, spanning hundreds of kilometers, would be obliterated in seconds. Entire cities, forests, and rivers would be vaporized, leaving behind a barren wasteland of blackened earth. The explosion would be so loud it could be heard thousands of kilometers away, shaking buildings and shattering windows in distant cities. The pyroclastic flows, superheated clouds of volcanic gas, ash, and debris, would race across the surrounding landscape at speeds of up to 700 kilometers per hour, 435 miles per hour. Unlike lava flows, which move slowly, pyroclastic flows would engulf everything in their path almost instantly, burning structures, melting metal, and suffocating any living thing caught in their grasp. The heat alone, often exceeding 1,000 degrees Celsius, 1,800 degrees Fahrenheit, would be enough to ignite wildfires and turn entire regions into a scorched, lifeless expanse. Meanwhile, the ash cloud would begin its slow but unstoppable spread. Unlike a typical volcanic eruption, which may send ash into the air for a few days, a supervolcano eruption would darken the skies for weeks, months, or even years. The dense, suffocating ash would collapse buildings, contaminate water supplies, and render entire cities uninhabitable. Even areas thousands of kilometers away would be affected, as microscopic ash particles infiltrated ventilation systems, water reservoirs, and electrical grids. Air travel would shut down worldwide. The thick ash would make it impossible for aircraft to fly, grounding commercial flights and cutting off vital supply chains. Airports would be buried under layers of fine, abrasive ash, which can destroy jet engines and corrode electronic systems. The global economy, already fragile, would experience an immediate crash, with stock markets plummeting and trade routes disrupted. But the worst was yet to come. As volcanic gases, primarily sulfur dioxide, SO2, were ejected into the stratosphere, they would mix with water vapor to form sulfate aerosols. tiny reflective particles that would begin to block out sunlight. Within days, the temperature would start to drop, marking the beginning of a volcanic winter. This period of global cooling could last for years or even decades, depending on the scale of the eruption. Crops would fail across the world, unable to grow in the drastically colder conditions. Widespread food shortages would trigger famine, with grain prices soaring and governments struggling to secure emergency supplies. The most vulnerable nations, those already reliant on food imports, would suffer first, but even the wealthiest countries would eventually feel the impact. The cooling effect could be as severe as 5 to 10 degrees Celsius, 9 to 18 degrees Fahrenheit, in some regions. This drop in temperature would disrupt monsoon cycles, weaken ocean currents, and destabilize weather patterns globally. Droughts would spread, while some areas would experience extreme flooding due to shifting jet streams and altered rainfall patterns. With food supplies dwindling, civil unrest would break out worldwide. Desperate populations would turn against their governments, triggering mass protests, riots, and potential wars over dwindling resources. Nations would compete for whatever fertile land remained, while refugees from the worst-hit areas, millions, perhaps even hundreds of millions, would seek shelter in less affected regions. Borders would close, economies would collapse, and once stable societies could descend into chaos. As the climate continued to deteriorate, ecosystems would struggle to adapt. Forests would wither, lakes and rivers would dry up, and entire species could go extinct. The oceans, already suffering from acidification and rising CO2 levels, could experience severe ecological shifts, with marine life dying off en masse. Coral reefs, which are already on the brink of collapse due to human activity, might vanish entirely. The economic toll of a supervolcano eruption would be incalculable. The 2022 eruption of the Hunga Tonga Hunga Hapai volcano, though relatively small compared to a supervolcano, caused billions of dollars in damage. A true supervolcano could cause trillions of dollars in losses, bankrupting governments and wiping out industries overnight. Global markets would collapse, inflation would skyrocket, and unemployment would reach record highs. But perhaps the most terrifying aspect of a supervolcano eruption would be its long-term consequences. Even after the volcanic winter subsided, the world would not simply return to normal. The landscape would be permanently altered, with vast regions uninhabitable due to thick ash deposits and lingering air pollution. The human population could be drastically reduced, with many areas suffering irreversible damage to their infrastructure and resources. Could humanity survive such an event? Perhaps. Modern technology, scientific knowledge, and international cooperation would give us an advantage that past civilizations never had. Emergency food stockpiles, underground shelters, and adaptive farming techniques could help some populations endure the worst of the crisis. However, global tensions could make cooperation difficult, and the sheer scale of destruction might push civilization to the breaking point. In the aftermath of the eruption, survivors would be left to rebuild in a world that had changed forever. Would governments rise to the challenge and create a new, more resilient society? Or would civilization fracture under the weight of disaster, plunging into an era of darkness and decline? In the next chapter, we will examine historical examples of societies that have faced volcanic disasters, from the fall of Pompeii to the collapse of the Minoan civilization, and what lessons they offer for humanity's future. By understanding how past civilizations were shaped, and sometimes destroyed, by volcanic events, we may gain valuable insight into how we might face the next great eruption. The supervolcanoes that shaped human history. Throughout history, volcanic eruptions have altered the course of civilizations, toppling empires, reshaping landscapes, and triggering mass migrations. While no recorded supervolcano eruption has occurred in human history, major volcanic events have provided glimpses into the devastation these colossal forces can unleash. From the fall of ancient cities to global climate disruptions, the story of humanity is deeply intertwined with the violent power of Earth's volcanoes. One of the most infamous volcanic disasters in history is the eruption of Mount Vesuvius in 79 AD, which buried the Roman cities of Pompeii and Herculaneum. Although Vesuvius is not a supervolcano, its sudden and catastrophic eruption demonstrated the deadly effects of pyroclastic flows, superheated waves of gas, ash, and rock that can obliterate everything in their path within seconds. Thousands of residents were caught in the disaster, their bodies preserved in hardened volcanic ash. The eruption was recorded by the Roman historian Pliny the Younger, providing one of the earliest first-hand accounts of a volcanic catastrophe. While Vesuvius was devastating on a local scale, some eruptions have affected the entire planet, plunging the world into years of hardship. One of the most severe in recorded history was the 1815 eruption of Mount Tambora in present-day Indonesia. Tambora's eruption ejected an estimated 160 cubic kilometers of ashen rock, making it the largest volcanic event in human history. The global consequences were catastrophic. The thick cloud of volcanic ash spread across the planet, blocking sunlight and dramatically lowering temperatures. 1816 became known as the year without a summer, as unseasonably cold temperatures led to crop failures and famine worldwide. In Europe and North America, freezing temperatures and persistent gloom devastated agriculture, leading to food shortages and mass starvation. Millions perished in the aftermath, and economic instability led to widespread social unrest. An even more ancient example of volcanic devastation can be found in the Thera eruption, which occurred around 1600 BCE in what is now Santorini, Greece. The eruption of this massive volcanic island produced tsunamis and climate changes that may have played a role in the downfall of the Minoan civilization, one of the most advanced societies of its time. Some scholars even suggest that the disaster may have inspired the myth of Atlantis, as described by the philosopher Plato. But none of these eruptions compare to the prehistoric supervolcanic events that shaped the early human experience. The most famous, and perhaps the most devastating, was the Toba supereruption, which occurred approximately 74,000 years ago in present-day Indonesia. Toba ejected an estimated 2,800 cubic kilometers of volcanic material, making it the largest eruption in the last 2 million years. The explosion sent so much ash into the atmosphere that it triggered a global volcanic winter, reducing temperatures by as much as 10 degrees Celsius, 18 degrees Fahrenheit. Some scientists propose that Toba's eruption nearly wiped out early humans, reducing the global population to as few as several thousand individuals. This theory, known as the Toba catastrophe hypothesis, suggests that the extreme cooling, food shortages, and environmental stress placed enormous pressure on early Homo sapiens, potentially leading to a genetic bottleneck, a sharp reduction in human genetic diversity. While the extent of Toba's impact on early humans remains debated, there is no question that it had severe consequences for life on Earth. The ash deposits from the eruption have been found as far away as Africa, India, and the Middle East, confirming that the event had a truly global reach. These historical and prehistoric eruptions provide critical insights into what might happen if a supervolcano erupted in the modern era. Unlike ancient civilizations, we have the advantage of scientific knowledge, technological advancements, and global cooperation, but we also face greater risks due to our interconnected world. Today, major volcanic eruptions can disrupt air travel, food supply chains, global markets, and entire economies. Even a relatively small event, like the 2010 Eyjafjallajökull eruption in Iceland, caused widespread flight cancellations across Europe, demonstrating how vulnerable modern infrastructure is to volcanic activity. If a supervolcano like Yellowstone or Toba were to erupt today, the consequences would be orders of magnitude worse than anything humanity has faced before. Understanding the past may be our best tool for preparing for the future. In the next chapter, we will explore the potential warning signs of a future supervolcanic eruption. By examining the latest research, scientific models, and historical patterns, we will assess whether Earth's most dangerous volcanoes are waking up, and whether humanity is truly ready for the next great eruption. The warning signs of a supervolcanic eruption. Supervolcanoes are not easy to predict. Unlike smaller volcanoes, which can show signs of activity leading up to an eruption, supervolcanoes often exhibit signs of unrest that can last for decades or even centuries without resulting in an eruption. However, scientists have learned to track subtle indicators that may hint at an impending eruption. While no eruption has been directly predicted yet, there are specific warning signs that could give humanity a chance to prepare before the worst happens. One of the most important indicators of an impending supervolcanic eruption is seismic activity. As magma rises from deep within the Earth, it causes underground pressure and movement, creating small earthquakes. These seismic tremors are not always dangerous in themselves, but their frequency and magnitude can be a sign that something much larger is brewing beneath the surface. Seismic activity is closely monitored in supervolcanic areas like Yellowstone, where a network of seismographs tracks even the smallest shifts in the Earth's crust. When magma begins to move, it can cause minor earthquakes that might not be felt by the population but could indicate that the system is becoming more active. In some cases, these tremors can escalate into more powerful quakes, signaling a buildup of pressure in the magma chamber. A sudden increase in seismic activity could be one of the first warning signs of a potential eruption. Along with seismic activity, ground deformation is another crucial indicator of volcanic unrest. Supervolcanoes are often located in large calderas, which are essentially collapsed volcanic craters. When magma begins to accumulate beneath the surface, the ground above the magma chamber will begin to rise, creating what is known as ground uplift. In places like Yellowstone, this rise is often subtle but consistent, with sections of the caldera slowly bulging upward over time. Increased ground deformation has been recorded in Yellowstone over the years, where parts of the caldera have risen by several centimeters annually. While this uplift is not an immediate cause for concern, it does suggest that magma is actively moving beneath the surface. Sudden and significant changes in ground deformation, such as rapid uplift or sudden subsidence, could be signs that an eruption is imminent. Monitoring the landscape with GPS sensors and satellite radar is essential to detect these changes early on. Another critical factor to consider is the emission of volcanic gases. As magma moves closer to the Earth's surface, it releases gases like carbon dioxide, CO2, sulfur dioxide, SO2, and hydrogen sulfide, H2S. These gases escape through fissures and vents in the Earth's crust, and their concentrations can tell scientists a lot about the behavior of a supervolcano. An increase in gas emissions can indicate that magma is nearing the surface and that the system is becoming more active. In areas like Campi Flegrei in Italy and Yellowstone, scientists closely monitor gas levels to track changes in volcanic activity. A sharp rise in sulfur dioxide emissions, for example, may be a sign that fresh magma is approaching the surface. Similarly, an increase in carbon dioxide emissions could indicate that the magma is stirring and that an eruption might be more likely. Though gas emissions alone are not definitive proof of an impending eruption, they are an important part of the puzzle. In recent years, scientists have also turned to satellite technology to monitor supervolcanoes from above. Using satellite imagery, researchers can observe vast stretches of land for signs of deformation, changes in heat patterns, and other indicators of volcanic unrest. For instance, thermal infrared imaging can detect changes in the surface temperature of a supervolcano, which might suggest the presence of rising magma beneath the surface. This data can be invaluable in tracking supervolcanoes over time and identifying potential trouble spots. One of the most promising technologies in volcanic monitoring is known as muon tomography. This technique uses high-energy particles called muons, which are produced when cosmic rays interact with the Earth's atmosphere. Muons can pass through solid rock, and by measuring how they are deflected or absorbed, scientists can create detailed images of the interior of a volcano, including its magma chamber. This method has been used to study volcanoes like Mount Vesuvius in Italy, and it holds great promise for future supervolcano monitoring. Muon tomography can help scientists determine the size and shape of magma chambers with great precision, providing valuable information about the stability and activity of a supervolcano. While all of these methods provide important clues, predicting the exact moment when a supervolcano will erupt remains extremely difficult. Supervolcanoes tend to erupt on a timescale that far exceeds human lifetimes, and many of the warning signs can occur long before any eruption takes place. For instance, the Yellowstone caldera has experienced periods of increased seismic activity and ground deformation for over a century, but there is still no definitive sign that an eruption is imminent. It's also important to remember that not all signs of unrest indicate an eruption. Many supervolcanoes, including Yellowstone, have experienced periods of activity without erupting. In fact, it's possible that some supervolcanoes may not erupt at all in recorded human history, despite exhibiting signs of volcanic activity. The unpredictability of supervolcanoes makes them all the more dangerous, as they could be quietly building toward an eruption or be in a dormant phase for thousands of years. With this in mind, scientists continue to improve their methods for monitoring supervolcanoes and refining their models for eruption forecasting. While we may not be able to predict the exact timing of a supervolcano eruption, the data collected from seismic activity, ground deformation, gas emissions, and satellite imagery can give us the best possible chance of detecting early signs of danger. In the event that a supervolcano is showing serious signs of an impending eruption, it is essential that governments, scientists, and emergency agencies work together to prepare. The scale of a supervolcanic eruption would be unlike anything humanity has faced, and timely action would be crucial to saving lives and minimizing the damage. Evacuations, resource management, and climate adaptation strategies would be essential in the aftermath of such a global disaster. In the next chapter, we will explore how humanity might cope with the aftermath of a supervolcanic eruption. From rebuilding economies and infrastructure to facing the challenges of a volcanic winter, we will look at the potential strategies that could help civilization survive and recover from one of the greatest catastrophes Earth could throw at us. The global impact of a supervolcano eruption. The eruption of a supervolcano would be a catastrophic event of a scale far beyond anything humans have ever witnessed. These eruptions are so powerful that they could change the course of history, affecting not just the region around the volcano, but the entire planet. The immediate consequences of such an eruption would be disastrous, but the longer-term effects would also pose serious challenges to life on Earth. In this chapter, we'll explore the global impact of a supervolcano eruption. When a supervolcano erupts, the first thing that comes to mind is the immediate destruction caused by the volcanic explosion itself. A supervolcanic eruption can eject thousands of cubic kilometers of magma, ash, and gas into the atmosphere. The force of the eruption is capable of leveling entire regions, triggering massive earthquakes, tsunamis, and landslides. The eruption of Yellowstone, for example, would devastate large portions of the United States, with ash fallout affecting much of North America. Beyond the immediate destruction, the ash cloud released by a supervolcano eruption would have a profound effect on the Earth's climate. When a massive eruption occurs, it injects large quantities of sulfur dioxide, SO2, and other aerosols into the stratosphere, where they can linger for months or even years. These aerosols reflect sunlight, creating a cooling effect on the planet's surface. This phenomenon, known as volcanic winter, can cause a significant drop in global temperatures. In the aftermath of the cooling effects of a volcanic winter could lead to widespread crop failures and food shortages. With shorter growing seasons and reduced sunlight, agricultural production would be severely impacted. In the case of the Yellowstone eruption, the ash fallout alone would blanket vast swaths of the United States, devastating farmlands and affecting food production on a massive scale. This, combined with the cooling effect from the volcanic aerosols, could lead to a global famine, with the most vulnerable populations. The loss of sunlight would also have a dramatic impact on ecosystems. Many species rely on consistent sunlight to regulate their biological processes, and a prolonged period of darkness would disrupt food chains. Plants would struggle to photosynthesize, leading to the death of herbivores, which in turn would affect carnivores. The collapse of ecosystems would be a catastrophic consequence of a supervolcano eruption, and it would take many years for life on Earth to recover, if recovery were even possible. While the eruption itself would be the most immediate and destructive consequence of a supervolcano, the long-term effects would also be severe. The climate change induced by the eruption could last for years, even decades. If the eruption were large enough, it could even trigger a new ice age. The cooling of the Earth's surface would lead to the expansion of glacier and ice sheets, further exacerbating the challenges faced by both human and animal populations. In a world already grappling with the devastating, another significant impact of a supervolcano eruption would be the disruption of global trade and transportation. The ash cloud produced by the eruption would likely ground flights for an extended period, affecting air travel worldwide. The ash fallout would also damage infrastructure, including roads, railways, and power lines, making it difficult to transport goods and resources. Supply chains would be severely disrupted, and economic activity would grind to a halt. In this scenario, even countries that are far, The economic consequences of a supervolcano eruption would be devastating. The destruction of infrastructure, combined with the global cooling and food shortages, would lead to massive economic disruptions. Businesses would be forced to shut down, and unemployment would rise sharply as industries struggle to operate in the aftermath of the eruption. Governments would face the challenge of providing for their citizens while also managing the international fallout of the disaster. The global economy would be T. Supervolcano eruptions would also lead to widespread health problems. The ash that is released into the atmosphere during an eruption can pose serious health risks, particularly for people living in the vicinity of the volcano. Respiratory problems, such as bronchitis and asthma, would become widespread due to the inhalation of fine ash particles. Even people living far from the eruption site would be at risk, as the ash cloud can travel vast distances, affecting air quality across entire continents. In Addi, the collapse of ecosystems and the loss of biodiversity would have a ripple effect on ecosystems and human societies around the globe. As species die off, the interconnected web of life that humans rely on for food, medicine, and other resources would begin to unravel. This could lead to a collapse in the availability of key natural resources, further exacerbating the difficulties that human populations face. Additionally, the loss of biodiversity would make ecosystems more fragile and less resilient to food. A supervolcano eruption would also have serious political consequences. Governments would need to coordinate efforts to provide emergency relief, manage evacuations, and rebuild infrastructure. The challenges of dealing with such a global crisis would strain political systems and international relations. Resources would become scarce, and nations would be forced to prioritize their own survival, potentially leading to conflict over food, water, and other essential resources. The international community, H. While the consequences of a supervolcano eruption would be catastrophic, humanity has shown remarkable resilience in the face of disaster. In recent years, there have been efforts to improve disaster preparedness and develop strategies for mitigating the effects of a volcanic catastrophe. The use of early warning systems, advanced monitoring technologies, and international cooperation could help reduce the severity of the impacts. However, even with these efforts, it is unlikely that humanity would escape. In the next chapter, we will explore the potential for survival following a supervolcano eruption. How could humans adapt to the new climate? What strategies could be employed to ensure the survival of our species in the face of such a global catastrophe? Let's take a closer look at the challenges and potential solutions for humanity's survival after the eruption of a supervolcano. Survival after a supervolcano eruption. The eruption of a supervolcano would be a global catastrophe, one that would shake the foundations of human civilization. With the potential to drastically alter the climate, destroy ecosystems, and disrupt the global economy, a supervolcano eruption would create a host of challenges for humanity. In this chapter, we explore the potential for survival in the aftermath of such an event, considering how human populations might adapt to a changed world and what strategies could be employed to ensure the survival of our species. The first and most immediate challenge that humans would face after a supervolcano eruption is the drastic shift in climate. As discussed in the previous chapter, the eruption would likely lead to a volcanic winter, with global temperatures plummeting due to the ash and aerosols released into the atmosphere. This cooling effect could last for years, severely disrupting agricultural production. The short growing seasons, reduced sunlight, and potential crop failures would create food shortages, leading to famine across much of the world. In such a scenario, survival would depend on access to food and water. Governments and international organizations would need to implement large-scale food distribution systems, with stockpiles of food being sent to the most vulnerable regions. Urban centers, in particular, would struggle to maintain their food supply as transportation networks are disrupted. Countries that are less reliant on agriculture or that are geographically isolated may have a slight advantage, but even they would face challenges as the global economy grinds to a halt. For those living in areas directly affected by the eruption, the situation would be even more dire. Ash fallout would bury entire cities, and the destruction of infrastructure would make it difficult to deliver aid. In this case, survival would depend on self-sufficiency. Communities would need to rely on whatever resources they have available, whether it's the ability to grow food in the face of harsh conditions or access to underground water sources. Survivalists and preppers, who have long anticipated the collapse of civilization, may find themselves more prepared than most to endure such a disaster. In the long term, the recovery process from a supervolcano eruption would be a slow and arduous one. It's likely that the planet's ecosystems would be severely disrupted, and many species would go extinct due to the climate change and food shortages. For humanity, this means that we would have to rebuild the world from scratch. The collapse of ecosystems would make it difficult to produce food, as the intricate relationships between plants, animals, and microorganisms would be shattered. This could lead to a new era of food scarcity, and humanity would need to develop alternative methods of food production, such as lab-grown meat or hydroponic farming. One of the most important aspects of survival in the aftermath of a supervolcano eruption would be the ability to maintain and rebuild infrastructure. Communication networks, transportation systems, and energy grids would all be severely damaged or destroyed. Governments would need to prioritize the restoration of these critical systems in order to help people reconnect with each other and access resources. While the damage to infrastructure may be extensive, history has shown that humanity is remarkably resilient when it comes to rebuilding in the wake of disasters. If we are able to establish sustainable energy sources, rebuild agricultural systems, and create new technologies for food production, it's possible that humanity could recover from such a devastating event. Another key factor in the survival of humanity after a supervolcano eruption would be the strength of social and political systems. A global catastrophe of this scale could lead to widespread unrest, as people scramble for resources and survival. Governments would need to work together, both nationally and internationally, to coordinate relief efforts and ensure that resources are distributed equitably. In the event of widespread political instability, countries might form alliances or compete for resources, which could lead to conflict. However, with the right leadership, cooperation, and a focus on long-term survival, it's possible that global cooperation could emerge in the face of such a challenge. The development of new technologies and innovations would be crucial for humanity's survival. In the aftermath of the eruption, the global need for renewable energy sources, sustainable food production, and efficient water filtration systems would be greater than ever. Scientists and engineers would need to work together to develop new ways of living in a drastically altered world. Innovations such as vertical farming, solar-powered desalination plants, and bioengineered crops could help humanity adapt to the changed environment. Additionally, advancements in space exploration might provide a backup plan, with the possibility of establishing colonies on other planets or moons to ensure the survival of the human species. Another factor to consider in the aftermath of a supervolcano eruption is the potential for future eruptions. Supervolcanoes, as we've learned, don't erupt on a regular schedule. In fact, they can remain dormant for thousands of years before showing any signs of activity. However, once a supervolcano erupts, the threat of further eruptions becomes a reality. The experience of surviving one eruption would mean that humanity would have to be prepared for the possibility of future events. Monitoring the activity of supervolcanoes and other volcanic hotspots would become a priority for scientists, and new methods of predicting eruptions could help humanity prepare for the next disaster. Efforts to improve early warning systems and evacuation plans would be essential in order to mitigate the effects of future eruptions. Ultimately, the question of survival after a supervolcano eruption is one of adaptation. Humanity has survived countless disasters throughout history, from earthquakes and tsunamis to pandemics and wars. Each time, we have found ways to rebuild and move forward. A supervolcano eruption would be one of the greatest challenges we've ever faced, but it is not beyond our ability to overcome. With preparation, cooperation, and innovation, it's possible that humanity could survive and even thrive in the aftermath of such a catastrophic event. In the next chapter, we'll explore the potential for humanity to develop strategies to prevent or mitigate the effects of a supervolcano eruption. What technological advancements or geoengineering solutions might we use to prevent such an event? Is there any hope for averting the devastation of a supervolcano eruption, or are we destined to face the consequences of these natural giants? Can we prevent a supervolcano eruption? The eruption of a supervolcano is one of the most devastating natural events that could occur on Earth. with the potential to drastically alter the climate, cause widespread destruction, and lead to the extinction of many species. It's no wonder that people have wondered if it's possible to prevent such a catastrophic event. While we currently don't have the technology to stop a supervolcano eruption, scientists are working on ways to better understand these enormous geological systems and develop methods for mitigating the potential consequences. In this chapter, we'll explore the possibility of preventing or mitigating a supervolcano eruption. Could humanity develop the technology to stop an eruption before it happens? Or, at the very least, could we find ways to reduce the scale of the disaster? We'll look at the current scientific understanding of supervolcanoes and the cutting-edge ideas that researchers are exploring. One of the key reasons why preventing a supervolcano eruption is so difficult is the sheer scale of these volcanic systems. Supervolcanoes are not like typical volcanoes, which tend to have a single vent or crater. Instead, supervolcanoes are massive, underground magma chambers that have the potential to erupt with incredible force. For example, the Yellowstone supervolcano is located in Wyoming, but its magma chamber stretches far beyond the national park and is capable of producing an eruption thousands of times more powerful than a typical volcanic eruption. The amount of magma stored beneath these volcanoes is enormous, and trying to control or release it in a controlled manner seems impossible with current technology. The most significant challenge when it comes to preventing a supervolcano eruption is predicting when one might happen. While smaller volcanoes can often be monitored for signs of imminent eruption, supervolcanoes are much more difficult to study. These systems are vast, with magma chambers that can be located many kilometers beneath the Earth's surface. By the time we see signs of an impending eruption, such as increased seismic activity, ground deformation, or gas emissions, it may be too late to take action. That said, scientists are working hard to develop better monitoring techniques to give us more time to prepare for a potential eruption. One promising method for detecting and monitoring supervolcanoes is the use of remote sensing technology. Tools such as satellites, drones, and ground-based sensors are already being used to monitor volcanic activity in real time. These tools can measure changes in temperature, ground movement, gas emissions, and seismic activity, all of which can provide valuable clues about the health of a supervolcano. By using these technologies, scientists can keep a close eye on the behavior of supervolcanoes like Yellowstone, Toba, and others. As the ability to monitor these systems improves, the hope is that we will have more advanced warning of any potential eruptions. Even with the best monitoring systems in place, however, there's no guarantee that we will be able to prevent an eruption. Given the scale of supervolcanoes, preventing an eruption may ultimately require geoengineering techniques, large-scale projects that alter the environment in order to influence the natural world. These techniques could, in theory, help reduce the likelihood or severity of an eruption, but they are still speculative and untested on such a large scale. One idea that has been proposed is to cool the magma chamber beneath a supervolcano. The theory is that by injecting water or other substances into the magma chamber, we could reduce the temperature of the magma, thereby reducing the pressure and preventing an eruption. While this sounds like a feasible idea in theory, the challenges of implementing such a technique are enormous. Injecting water into the Earth's crust would require drilling deep into the ground, possibly several kilometers down. Even if this could be done, there's no guarantee that it would be effective, and the potential consequences of such an intervention could be unpredictable. Another potential geoengineering approach to preventing a supervolcano eruption is to control the flow of magma. The idea behind this technique is to find ways to safely release pressure from the magma chamber before it reaches dangerous levels. One possibility could involve creating a series of controlled vents or fissures that allow the magma to escape gradually, thereby reducing the buildup of pressure. However, creating such vents would require precise knowledge of the magma chamber and the ability to drill into the Earth in a controlled manner. Furthermore, there's a risk that attempting to control the flow of magma could trigger an eruption rather than prevent one. A more radical idea is to use nuclear explosions to prevent a supervolcano eruption. The theory behind this approach is that detonating a series of nuclear bombs beneath the Earth's surface could relieve the pressure in a supervolcano's magma chamber, thereby preventing an eruption. This concept, while it may sound like something out of a science fiction novel, has been seriously considered by some scientists. The idea is based on the fact that nuclear explosions have the potential to create large-scale fractures in the Earth's crust, which could, in theory, allow the magma to escape safely. However, the risks associated with such a strategy are enormous, and it's unclear whether this would actually work. It's also worth noting that using nuclear weapons in this manner would come with a host of ethical, environmental, and political concerns that would need to be addressed. Aside from geoengineering, another potential solution for preventing or mitigating the effects of a supervolcano eruption lies in preparation. While we may not be able to stop a supervolcano from erupting, we can certainly take steps to prepare for it. For example, early warning systems could help us identify signs of an impending eruption, giving us time to evacuate people from affected areas. Governments could also stockpile food, water, and medical supplies in case of a disaster, and researchers could develop technologies to help us survive the harsh conditions that would follow an eruption. There's also the possibility of developing technologies that could help us cope with the long-term effects of a supervolcano eruption. For example, new agricultural techniques, such as vertical farming or lab-grown meat, could help ensure a steady food supply in the aftermath of a volcanic winter. Advances in renewable energy sources, such as solar or wind power, could help provide electricity in areas where traditional power grids have been damaged. Additionally, breakthroughs in water filtration and desalination could help mitigate the impact of disrupted water supplies. In the end, preventing a supervolcano eruption may be beyond our current technological capabilities. However, by improving our understanding of these powerful natural systems and developing new monitoring techniques, geoengineering solutions, and survival strategies, humanity can increase its chances of surviving such a disaster. The key to our survival may not be in preventing the eruption itself, but in preparing for the aftermath. In the next chapter, we will look at some of the most well-known supervolcanoes in the world and examine their history, potential for eruption, and the research being done to monitor and study them. How likely are these supervolcanoes to erupt in the near future? The world's most dangerous supervolcanoes. Supervolcanoes are the most destructive geological forces on Earth, capable of causing catastrophic events that could alter the course of human history. Although these enormous volcanic systems are rare, they are scattered across the globe, each one holding the potential to unleash unimaginable devastation. In this chapter, we'll take a closer look at some of the most dangerous supervolcanoes in the world, examining their history, their potential for future eruptions, and what scientists are doing to monitor them. One of the most well-known and closely studied supervolcanoes is the Yellowstone supervolcano, located in the Yellowstone National Park in the United States. Yellowstone is perhaps the most famous supervolcano in the world due to its proximity to populated areas and its potential for a catastrophic eruption. The Yellowstone supervolcano has erupted 3 times in the past 2.1 million years, with the most recent eruption occurring around 640,000 years ago. Each of these eruptions was an event of enormous scale, releasing tens of thousands of cubic kilometers of magma and ash into the atmosphere. Although Yellowstone has not erupted in over 600,000 years, scientists continue to monitor the region for signs of increased volcanic activity. The area is characterized by geothermal features such as geysers, hot springs, and fumaroles, which are a result of the underlying magma chamber. While there is no indication that an eruption is imminent, scientists are keenly aware of the potential dangers posed by Yellowstone. The U.S. Geological Survey, USGS, conducts regular monitoring of seismic activity, ground deformation, and gas emissions in the region. These monitoring efforts are crucial for detecting any signs of impending eruptions. One of the key factors in studying Yellowstone is understanding the behavior of the magma chamber beneath the park. This magma chamber is vast, extending beneath much of the park and containing an enormous amount of molten rock. The chamber is also located relatively close to the Earth's surface, which makes it more susceptible to changes in pressure and temperature. Scientists use various methods to study the magma chamber, including seismic imaging and geophysical surveys, to better understand its behavior and potential for future eruptions. Despite the regular monitoring efforts, the chances of an eruption occurring at Yellowstone in the near future remain low. According to the USGS, the probability of a supervolcanic eruption at Yellowstone occurring in the next few thousand years is extremely small. However, the risk, however remote, has led to significant public interest in the supervolcano, and there are ongoing efforts to develop better monitoring techniques to detect any signs of eruption before it's too late. Another supervolcano that has attracted considerable attention is the Toba supervolcano, located on the island of Sumatra in Indonesia. The Toba eruption, which occurred around 74,000 years ago, is considered to be one of the largest volcanic eruptions in Earth's history. This eruption released an estimated 2,800 cubic kilometers of ash and magma, resulting in a global climatic event known as the Toba supereruption. The eruption caused a dramatic decrease in global temperatures, leading to a volcanic winter that lasted for several years and caused widespread disruption to ecosystems and human populations. The Toba eruption is also associated with a significant bottleneck in human evolution. It is believed that the eruption may have caused a genetic bottleneck in human populations, reducing the global population to just a few thousand individuals. This event may have played a role in shaping the genetic diversity of modern humans and may have had lasting impacts on the development of human civilization. Today, the Toba supervolcano is considered to be one of the most dangerous volcanic systems on Earth. The caldera left behind by the eruption is vast, spanning over 100 kilometers in diameter. While there are no signs of imminent eruption, scientists continue to monitor the area for signs of volcanic activity. The Indonesian government and various international organizations have invested in monitoring and research to better understand the behavior of the Toba system and to assess the potential risks associated with future eruptions. In addition to Yellowstone and Toba, there are several other supervolcanoes around the world that pose a significant risk to global stability. The Long Valley caldera, located in California, is another supervolcano that has the potential to produce a catastrophic eruption. The Long Valley eruption, which occurred around 760,000 years ago, released a massive amount of volcanic material, and the caldera remains an area of active study for scientists. While the probability of a large eruption at Long Valley is low, the presence of geothermal features, including hot springs and fumaroles, indicates that the underlying magma chamber is still active. The Campi Flegrei supervolcano, located near Naples in Italy, is another active volcanic system that has raised concerns about its potential for a catastrophic eruption. The Campi Flegrei caldera has erupted multiple times in the past, with the most recent eruption occurring around 40,000 years ago. The region around Campi Flegrei is densely populated, and any eruption could have devastating consequences for the surrounding communities. Scientists are closely monitoring the area for signs of increased volcanic activity, and the region has been identified as one of the most hazardous volcanic areas in Europe. The Taupo volcanic zone in New Zealand is another supervolcano that scientists are keeping an eye on. The most recent eruption at Taupo occurred around 1,800 years ago and was one of the most explosive eruptions in recorded history. While there have been no signs of an imminent eruption at Taupo, the region remains an area of active volcanic activity, and scientists continue to study the magma chamber beneath the surface. Lastly, the Aso caldera in Japan is another supervolcano that has the potential to produce a major eruption. The Aso caldera is located on the island of Kyushu and is one of the largest volcanic calderas in the world. The Aso system has experienced multiple eruptions over the past 300,000 years, and while the region is not currently experiencing signs of imminent eruption, it remains an area of ongoing research and monitoring. The existence of these supervolcanoes highlights the global risks posed by these massive volcanic systems. While we may not be able to prevent an eruption from occurring, ongoing monitoring and research are critical to understanding the behavior of supervolcanoes and preparing for any potential eruptions. By studying the history of these volcanic systems and developing better monitoring technologies, we can increase our chances of detecting early warning signs and responding to potential eruptions before they become catastrophic events. In the next chapter, we will explore the potential long-term effects of a supervolcano eruption on global ecosystems. What would the impact be on plant and animal life? How would the eruption alter the Earth's climate? And what steps can be taken to mitigate the damage to biodiversity? The long-term effects of a supervolcano eruption on ecosystems. The eruption of a supervolcano would not only be a catastrophic event for human civilization, but would also have profound, long-lasting effects on global ecosystems. Supervolcanoes have the potential to release vast amounts of ash, gas, and debris into the atmosphere, causing climate disruptions that could last for decades. In this chapter, we'll explore the potential long-term effects of a supervolcano eruption on ecosystems, including how it would affect plant and animal life, as well as the Earth's climate. When a supervolcano erupts, it releases an enormous amount of material into the atmosphere. This can include ash, gases like sulfur dioxide, carbon dioxide, and water vapor, and large amounts of volcanic aerosols. These materials can have significant effects on both the local and global environment. One of the most notable effects is the impact on the climate. The ash and gases released during a supervolcano eruption can block sunlight, leading to a dramatic drop in global temperatures. This phenomenon, known as a volcanic winter, can cause a sharp cooling of the Earth's climate for years or even decades after the eruption. A volcanic winter can have disastrous effects on ecosystems. The decrease in sunlight and lower temperatures can reduce the ability of plants to photosynthesize, disrupting food chains and leading to widespread crop failures. The cooling effect on the climate would also affect weather patterns, making certain regions colder and others drier. This could lead to the collapse of ecosystems that rely on stable climates, particularly those in temperate and tropical regions. Plant life would be severely impacted by the effects of a supervolcano eruption. The lack of sunlight caused by ash clouds and aerosols would stunt plant growth, especially in regions near the eruption. Even areas far from the eruption could experience reduced sunlight and cooling temperatures, which would hinder agricultural productivity. Plants are the foundation of many ecosystems, so a reduction in plant life would lead to cascading effects throughout the food web. Herbivores would find it harder to find food, and predators that rely on herbivores would also struggle to survive. In addition to affecting plant life, the eruption of a supervolcano would likely cause massive disruptions in animal populations. Many species are dependent on specific environmental conditions, and sudden shifts in climate can lead to habitat loss, migration, and population declines. For example, animals that rely on stable temperatures or seasonal cues for migration and reproduction would be impacted by the changes caused by the eruption. Some species might be able to adapt to the changing conditions, but others, especially those that are highly specialized, may face extinction. The global effects of a supervolcano eruption would also have significant consequences for marine ecosystems. The ash and gases released during the eruption could be carried by winds and rain, eventually settling into oceans and other bodies of water. The particles in the atmosphere could lead to ocean acidification, making it harder for marine organisms like corals, shellfish, and plankton to survive. These organisms are key components of marine food webs, and their decline would have far-reaching impacts on marine life. Additionally, the cooling of the Earth's climate could alter ocean currents, affecting the distribution of marine species and disrupting ecosystems on a global scale. One of the most significant consequences of a supervolcano eruption would be its potential to drive a mass extinction event. Mass extinctions occur when large numbers of species go extinct over a relatively short period of time due to rapid and extreme environmental changes. The effects of a supervolcano eruption, ranging from climate change to the loss of habitats and food sources, could trigger such an event. The most famous example of this is the Permian-Triassic extinction event, which occurred around 252 million years ago and is thought to have been caused in part by massive volcanic activity. A supervolcano eruption today could have similar impacts, driving many species to extinction and drastically altering the course of evolution. While supervolcanoes are capable of causing widespread environmental destruction, the effects on ecosystems might not be uniformly negative. Some species might be able to adapt to the changing conditions, while others could take advantage of the disruptions to thrive. For example, after a major volcanic eruption, certain species of plants and animals might move into areas that were previously inhospitable. These species might thrive in the newly available resources, leading to the emergence of new ecosystems. Over time, life on Earth would begin to recover, and new species would evolve to fill ecological niches that were left vacant by the extinction of others. In the aftermath of a supervolcano eruption, ecosystems would likely undergo a long period of recovery. The cooling effect on the climate would persist for years, and it could take decades for plant and animal populations to return to pre-eruption levels. The recovery of ecosystems would depend on a variety of factors, including the severity of the eruption, the extent of the environmental changes, and the adaptability of species. In some cases, ecosystems may never fully recover to their previous state, and new types of ecosystems could emerge in response to the changing climate and environmental conditions. One of the most important factors in the recovery of ecosystems after a supervolcano eruption would be the ability of species to adapt to the new environment. Species that are able to tolerate colder temperatures, reduced sunlight, and altered food sources would have a better chance of surviving. However, species that are highly specialized or dependent on specific environmental conditions might struggle to adapt and could face extinction. This highlights the importance of biodiversity in maintaining the resilience of ecosystems. A diverse range of species can help ecosystems recover more quickly by providing a variety of functions and resources, making the overall system more adaptable to changes. The recovery of ecosystems after a supervolcano eruption would also depend on the time frame over which the eruption occurs. While some ecosystems might recover in a few decades, others may take centuries or even millennia to return to their previous state. The effects of a supervolcano eruption could also have long-lasting impacts on the Earth's biogeochemical cycles. For example, the release of large amounts of carbon dioxide and sulfur dioxide into the atmosphere could alter the carbon cycle, leading to shifts in atmospheric conditions, weather patterns, and the distribution of plant and animal species. In the long term, the Earth's ecosystems would likely recover from a supervolcano eruption, though the process would be slow and uneven. Over time, life would adapt to the new conditions, and new species would emerge to fill ecological roles. However, the immediate aftermath of a supervolcano eruption would be devastating for many species, including humans. Understanding the long-term effects of supervolcanoes on ecosystems can help us better prepare for such events and mitigate their impacts. In the next chapter, we will explore the human impact of a supervolcano eruption. How would a supervolcano eruption affect human society, and what steps can we take to survive such a catastrophic event? The human impact of a supervolcano eruption. The eruption of a supervolcano would be one of the most catastrophic events humanity could face. Unlike typical volcanic eruptions, which may cause localized devastation, supervolcano eruptions have the potential to affect the entire planet. From the immediate destruction caused by the eruption itself to the long-term consequences of climate shifts and environmental damage, the human impact of a supervolcano eruption would be profound. In this chapter, we will explore the potential effects of a supervolcano eruption on human society and examine the ways we might be able to prepare and survive such an event. A supervolcano eruption would likely cause widespread destruction in the immediate vicinity of the eruption. The eruption itself could release an enormous volume of volcanic ash, gases, and pyroclastic flows. These volcanic materials could blanket large portions of the Earth, especially in regions close to the eruption. Cities and towns near the eruption would be devastated by the forces of the explosion, with buildings collapsing from the weight of ash and the effects of pyroclastic flows. The heat from the eruption would cause wildfires, while ash clouds would block out sunlight, leading to a dramatic drop in temperature. The volcanic ash would contaminate water sources and crops, making it difficult for survivors to find clean water and food. The immediate impact on human populations would be catastrophic. Those living near the eruption would likely not survive, as the eruption would be violent and unpredictable. Thousands, if not millions, of people could be killed in the first few days or weeks after the eruption. The ash and gases released into the atmosphere would pose serious health risks to people even at much greater distances. The ash could cause respiratory problems, especially in vulnerable populations such as children, the elderly, and those with pre-existing health conditions. The effects of inhaling volcanic ash could lead to long-term health issues, including lung damage and respiratory infections. In addition to the health risks posed by volcanic ash, the eruption would also disrupt critical infrastructure. Roads, airports, and railways would be rendered impassable by thick layers of ash, while power lines and communication networks would be knocked out. This would make it difficult for governments and aid organizations to deliver assistance to affected areas, leaving many people stranded without food, water, or medical care. The collapse of transportation and communication systems would also make it harder for survivors to evacuate, compounding the devastation and loss of life. The longer-term effects of a supervolcano eruption would be even more far-reaching. The eruption would release large amounts of gases, such as sulfur dioxide, into the atmosphere. These gases would combine with water vapor to form sulfuric acid, which would contribute to a cooling of the Earth's climate, a phenomenon known as a volcanic winter. The cooling effect could last for several years, potentially causing global temperatures to drop by several degrees. This would have widespread effects on agriculture, as shorter growing seasons and colder temperatures would make it difficult for crops to thrive. Food shortages would be a significant problem, leading to malnutrition and famine in many parts of the world. The reduction in sunlight caused by ash and aerosols in the atmosphere would also disrupt photosynthesis, further diminishing crop yields. In addition, the cooling of the Earth's climate could lead to harsher winters and more severe weather patterns, making it even harder for agricultural systems to recover. The global food supply would be severely impacted, leading to widespread starvation, economic collapse, and social unrest. Governments might struggle to maintain order as resources become scarce, leading to increased conflict and instability. The eruption of a supervolcano could also have profound effects on human migration patterns. As regions become uninhabitable due to ash fallout, food shortages, and extreme weather, large numbers of people would likely be forced to flee their homes in search of safety and resources. This could result in large-scale migrations, placing enormous pressure on neighboring countries and regions. The movement of refugees could create new political and social challenges, as nations struggle to accommodate displaced populations. The economic consequences of a supervolcano eruption would also be severe. In addition to the direct damage caused by the eruption itself, the long-term disruption of global trade, agriculture, and industry would lead to economic collapse. Stock markets would likely plummet, and the global economy would enter a period of deep recession or depression. The cost of rebuilding after a supervolcano eruption would be astronomical, and many countries would find it difficult, if not impossible, to recover. International aid would be crucial, but the scale of the disaster could overwhelm even the most well-prepared nations. One of the greatest challenges posed by a supervolcano eruption is the potential for a prolonged collapse of human society. The eruption would disrupt global supply chains, leading to shortages of essential goods such as food, medicine, and fuel. In the aftermath, the rebuilding process would take decades, if not centuries, and human civilization would face significant setbacks. Modern technology and infrastructure, which rely on global trade and cooperation, would be severely disrupted. In many parts of the world, the development of cities and advanced societies could be set back by centuries, with much of the population returning to a more subsistence-based existence. However, it is important to note that human resilience and adaptability have allowed us to survive previous natural disasters, and we would likely find ways to adapt to the challenges posed by a supervolcano eruption. The key to survival would lie in preparation, planning, and cooperation. Governments and international organizations could take steps to mitigate the impact of such an event, including investing in early warning systems, strengthening infrastructure, and improving disaster response capabilities. One of the most important aspects of preparing for a supervolcano eruption would be developing a global strategy for disaster relief. International cooperation would be crucial in ensuring that resources are distributed efficiently and that aid reaches the most affected regions. Governments could also invest in disaster resilience by improving infrastructure and creating more robust supply chains that are better able to withstand disruptions. Stockpiling food, water, and medical supplies in strategic locations would help ensure that there is enough aid available in the aftermath of a supervolcano eruption. Another potential strategy for mitigating the effects of a supervolcano eruption is to invest in technologies that could reduce the impact of volcanic ash and gases on the environment. Scientists are researching ways to capture and neutralize volcanic gases before they can reach the atmosphere, which could help mitigate the cooling effects of a volcanic winter. Additionally, developing agricultural techniques that are more resilient to cold temperatures and low light levels could help mitigate the effects of reduced crop yields. In the next chapter, we will explore the role of science and technology in monitoring and studying supervolcanoes. The science and technology of monitoring supervolcanoes. As we've explored throughout this video, supervolcanoes represent one of the most dangerous and unpredictable threats to human civilization. Their eruptions are capable of causing widespread destruction, long-lasting environmental damage, and even the collapse of societies. However, despite their catastrophic potential, supervolcanoes remain difficult to predict, and our understanding of them is still evolving. In this final chapter, we'll explore the science and technology that is being used to monitor these massive volcanic systems and attempt to predict their behavior, so that we can better prepare for the potential disaster they pose. The study of supervolcanoes is a relatively young field within volcanology, and scientists are only just beginning to understand the complex processes that drive these massive eruptions. Unlike typical volcanoes, supervolcanoes have eruption cycles that span hundreds of thousands to millions of years, making it difficult to study them in real time. This long cycle means that supervolcanoes often lie dormant for long periods, sometimes for tens of thousands of years, making it hard to know exactly when they might erupt again. To monitor supervolcanoes, scientists rely on a combination of geological, geophysical, and geochemical techniques. By analyzing the physical properties of the Earth's crust and the gases released by volcanic systems, scientists can detect signs of volcanic activity and assess the potential for an eruption. One of the most important tools used in this process is the study of seismic activity. Seismometers are placed in and around volcanic regions to measure the movement of tectonic plates and any vibrations caused by the movement of magma beneath the surface. If there is an increase in seismic activity, it could indicate that magma is rising toward the surface, a potential precursor to an eruption. In addition to monitoring seismic activity, scientists also use ground deformation measurements to track changes in the shape of the Earth's surface. As magma moves beneath the surface, it can cause the ground to swell or shift. By using techniques such as GPS and satellite imagery, scientists can monitor these subtle changes in the land surface and detect any signs of volcanic unrest. If a supervolcano is inflating, it could be an indication that magma is accumulating and that the volcano might be primed for an eruption. Another important aspect of supervolcano monitoring is the study of gases emitted by the volcano. Volcanic gases, such as sulfur dioxide, carbon dioxide, and water vapor, are key indicators of the volcanic system's behavior. Scientists use specialized equipment to collect and analyze gas samples from fumaroles, vents that release gas, and other emissions points around the volcano. Changes in the composition or volume of gases can indicate that magma is approaching the surface and that an eruption might be imminent. For example, an increase in carbon dioxide emissions could suggest that magma is releasing gas as it rises through the Earth's crust. One of the more advanced tools used in monitoring supervolcanoes is called muon tomography. This technique relies on cosmic rays, which are high-energy particles that constantly bombard the Earth's atmosphere. These particles, known as muons, can penetrate through solid rock and help scientists map the density of the Earth's interior. By analyzing how muons pass through the volcanic system, scientists can gain insight into the structure of the volcano, including the size and location of magma chambers. Muon tomography is a relatively new technique, but it has the potential to provide valuable information about the behavior of supervolcanoes and help predict future eruptions. Additionally, the study of paleovolcanism, analyzing ancient volcanic eruptions, is an essential part of understanding supervolcanoes. By studying the deposits left behind by previous eruptions, scientists can gain a better understanding of how supervolcanoes behave over long periods of time. This can help them develop models that predict when a supervolcano might erupt next and how severe the eruption could be. Studying ancient eruptions also allows scientists to track the long-term effects of supervolcano eruptions on the environment, which can help us better understand the potential consequences of future events. One of the most important areas of research in the field of supervolcano monitoring is the development of early warning systems. An early warning system for supervolcanoes would provide scientists with the ability to detect volcanic unrest at the earliest possible stage, potentially giving communities time to evacuate and prepare for the eruption. However, due to the long dormancy periods of supervolcanoes, there is still much uncertainty about how to predict their behavior accurately. Scientists are working on refining their monitoring techniques and improving the accuracy of eruption forecasting, but predicting the eruption of a supervolcano remains a challenge. In recent years, scientists have made significant progress in developing better models for predicting volcanic eruptions. These models incorporate a wide range of data, including seismic readings, gas emissions, ground deformation measurements, and temperature changes. By analyzing this data, Scientists can create more accurate models of how magma behaves beneath the Earth's surface and use these models to predict when a supervolcano might erupt. However, even with the best models, predicting the exact timing and magnitude of a supervolcano eruption remains a difficult task. One of the challenges scientists face in predicting supervolcano eruptions is the lack of historical data. Because supervolcanoes erupt so infrequently, there is a limited amount of data available to help scientists understand their behavior. In addition, the eruptions of supervolcanoes are often preceded by subtle signs that are difficult to detect. The early warning signs of an impending eruption might be similar to normal volcanic activity, making it difficult to distinguish between a harmless increase in seismic activity and a potentially catastrophic eruption. Scientists are working to develop more sophisticated methods for detecting these early signs, but the unpredictable nature of supervolcanoes makes forecasting difficult. Despite the challenges, there is hope that with continued research and technological advancements, scientists will be able to improve their ability to monitor and predict the behavior of supervolcanoes. The development of new technologies and better monitoring techniques, combined with a deeper understanding of volcanic processes, will increase our chances of detecting an eruption. In conclusion, the monitoring of supervolcanoes is a complex and ongoing process, but scientific advancements are helping to improve our understanding of these dangerous natural systems. By combining a variety of monitoring techniques, such as seismic readings, gas analysis, ground deformation measurements, and muon tomography, scientists are working to develop more accurate predictions for when supervolcanoes might erupt. While we may not yet have the ability to predict exactly when and where a supervolcano will erupt, continued research and technological innovations will provide us with better tools to prepare for the potential disaster. The more we learn about these giants beneath the Earth's surface, the better we can protect ourselves and ensure that we are ready when the next eruption occurs.